they're talking. Yeah.
Quiet coyotes are
Yeah.
How'd you get the door? Oh, he let you in. I was so confused. I was like, am I door locked? Alright. Yeah, I got you. Here you go. Alright guys, be quiet. I'm talking now. So, first thing we're going to talk about with continuity is going to be the three different types of discontinuity that you're going to see come up, okay? There's point discontinuity. This is where the function looks like it could be continuous, except for there's one point that's either completely removed or it's basically shifted up, okay? And that's point discontinuity. It's a hole, okay? Then we have infinite discontinuity, and it's called infinite because it exists infinitely at that x value because it's a vertical asymptote. Okay, so it's like the vertical asymptote comes through and cuts the function infinitely into two parts. Okay? And then jump discontinuity is similar to like what a piecewise function has, where as you can see there's space right here on the y. They're not lined up. Okay? So that's what jump discontinuity looks like. It's a break. Okay? Alright. So first thing you need to know is the definition of continuity at a point. So the definition of continuity states that the point has to exist. Okay, so the point has to be defined, and the limit on both sides has to match whatever that point is. Okay. So that's essentially what this says. You have to look at the limit and the function and if they match. So something that's continuous is like something like, say, this. Okay? If I were to check the limit at 1, it's continuous at 1 because the function's defined at 1 and the limit is the same thing as the function. So that's what that's asking. Alright, so example 1 gives you a picture and it asks you to identify where the function is discontinuous. So it's discontinuous at x equals 1. Where else is it discontinuous? X equals 3, and lastly x equals 5. So this is point discontinuity. This is jump discontinuity. So, yeah. Alright, so the next question says, does the limit as x approaches 5 equal the function defined at 5? What do you guys think? No. Because the limit approaches 1, but the function is defined at what value? 2. So the answer is no. What value should be assigned to f of 5 to make it continuous? So if I told you that we could move this point around, where could we put it to make the function continuous?
1.
Good. So if we moved it to 1, it would now be a continuous function at that point. Nothing. You're good. Alright, so this question here says, find the point of discontinuity and determine if it is removable. So this is a piecewise function. So we're going to graph it. So our reminder is that this piece of the piecewise function only exists where x is less than 2. So I'm going to highlight that part in pink. And then this part of the function only exists where x is greater than or equal to 2. So for the first part, this is a linear function, right? So to graph a linear function, we start at the
0, 0.
no.
Dang it.
The y
Intercept.
intercept on the y-axis. Yes, very good. You're both kind of right.
Is
So we start at -2. No. And then we go use the slope up 2 over 1. The slope is 2, right? Up 2 over 1. But here you're going to notice I'm putting an open circle. Why did I put an open circle? Yeah, because see how the inequality says only x where it's strictly less than 2? So it's not actually defined at 2. And then from here you can just connect the dots and draw a line. And that line is infinite on one end and finite on the other. Does anyone remember what this looks like when it's just like f of x equals a number, like 3?
Straight across.
Straight across, good. So basically we have a straight line at 3. So we have an open or closed circle, and then we go straight across at 3. And the reason that circle is filled is because the inequality says x is greater than or equal to 2. So what type of discontinuity is this right here? It's at what value is the discontinuity?
2.
And what kind of discontinuity is it? It's jump, so it's definitely not removable, right? Removable would be if it was like a pole removed, but this is jump discontinuity. Okay. So what we're going to learn now is how we can fix jump discontinuity by actually changing one of the equations. So let's say, for example, instead of this equation having a y-intercept at -2, what if this equation stayed the same elsewise but had a y-intercept at 1? Wouldn't that shift every point up by 1 unit?
Yes.
So you don't have to graph this, but imagine if all these points shifted up 1 unit. Would it still be discontinuous if that were the case? No, I could fix it, right? So we're going to learn about how we can do that. Okay, so first thing we have here is this function, and it's a discontinuous function, and we're going to define the function so that it is continuous. We're going to figure out what type of discontinuity this function has. So step 1 to doing that is to factor it. So what is the numerator going to factor into?
X plus 5, x minus 5.
Good. The denominator's a minus. I don't know why I put that there. So it's x plus 5, x minus 5. And you're at the point where you could now cancel out the x minus 5s, right? However, we want to first figure out what type of discontinuity this creates. So what type of discontinuity is this when it gets removed? It's as obvious as it's removable discontinuity, which creates a hole, right? So we know that we have a hole at what x value?
5.
Regular 5. Okay. So all that's left of the function now is just y equals x plus 5. What type of function is that? Is it quadratic? Is it cubic? Is it linear?
Linear.
It's linear. Good. So in that case, we have a linear function, but there's just one problem. It has a hole at the x value of 5. So of course that hole exists at a certain y value, right? So we're going to end up figuring out what that is. So to define our function and make it continuous, here's what we do. We take the part of the function that we just solved for, and we know that this function can exist everywhere except for what x value? 5. Now we need to fill the hole at 5. So we know that at 5 we need to plug that hole. We need to figure out what y value that needs to happen at. So in order to figure that out, we're going to take our function and plug the hole into the function. And that gives us what?
10.
Good. So what that means is, if I were to graph just this portion of the function right here, I would have a hole at 5. But if I then graph this piece too, this is just a point, I now have filled that hole that the function originally had. Make sense? Okay. All right. So now we're trying to figure out what the y-intercept of this function could be so that the function is continuous and doesn't have jump discontinuity. So we can actually use algebra to do this. We know that if there is discontinuity, that the discontinuity would exist at what x value?
2, 5?
It would have to just exist, just the x value is what we know. We know that the function has some type of switch over at 2, right? So I know that at 2 the function's switching from one to the other. It's going to like change into another function. So what we want to happen at that point is we want it to line up on the y, to do it at the same y, okay? So how we can make that happen is we can actually set the two pieces of these functions together because we want them to exist at the same y value. And then when we do that, we know the x value that it has to occur at is 2, so we can actually plug 2 in for x. Like this. So what is 2 plus 3? 5 equals 6 minus c. So that means that we subtract 6 on both sides. We get 5 minus 6, which is negative 1. So c equals what? 1. Okay. Oh, I made a mistake here. You guys see what it is? I was like, this is not what I got earlier. Yeah, sorry about that. I plugged in 3 instead of 2. I don't know why I did that. So this should be this, which is 1 equals negative c, which c is equal to negative 1. Sorry about that. Okay. So what that means is, if this c was negative 1, these functions would line up properly, okay? So that means that this piece of the function would have to be 2x plus 1. Do you all see why it's plus 1? Because if you plug a negative into that negative, it's going to become a positive. Okay. So now we're going to graph these two pieces of the function. So So this one here exists where x is less than 2. And the other one exists where x is greater than 2. Here. So to graph the first one, I start at my y-intercept and I go up 1 over 1. Until I get here where the boundary is, where I'm going to draw an open circle, because the function doesn't actually touch at 2. Everyone good with that? Okay. So now for the other piece of the function, I know that basically I could start at my y-intercept of 1, but the graph doesn't actually exist there, right? So we can do like mock graphing, or you can plug in points, whatever you feel more comfortable with. So if I start here at 1, I would technically start at 1 and go up 2 over 1, up 2 over 1, until I get here, which is the first defined point. And then I would go up 2 over 1 again. So did the algebra work? Did we end up filling the hole on the other function? Do we have any discontinuity anymore? No. You see how we were able to fix that with algebra? Okay, perfect. All right, so now we're going to do one that is a two-piece or three-piece situation where basically we have to make sure all 3 pieces line up. So this is like, say you had something like this. Let me show you an example. So say you had a piecewise function that looked like this. You want to make it look like this. So they're all connected. You guys see what I'm saying? So we're going to make that happen using algebra. Okay. So step 1 is we need these 2 pieces right here to be set equal to each other first. So we're going to set 2 equal to ax plus b. And what we need to figure out is what x value do we want them to meet at, these 2? Well, one picks up where the other one leaves off at -1. So you're going to plug -1 in for x here, which gives you -a plus b. So I plugged in -1 for x. Is everybody good with how we got 2 equals -a plus b? Okay. Now we're going to do the same thing with these 2 pieces, because remember, these 2 pieces meet up. So I'm going to set these 2 equal to each other as well. But when I do that, what value am I now going to be plugging in for x? 3, because that's where those 2 pieces meet. So that gives me 3a plus b. So is everyone good with how we got this and how we got this? Okay. So we have to solve this system basically like it's x and y with the a and b. So you have 2 options. You can either use substitution or what's the other method? Well, either way you're using the method still, right? Elimination, right? So you can use substitution or elimination to solve. I'm going to use substitution, but you can use whatever one you want. So to do substitution, I'm going to add a to both sides on this one. That gives me 2 plus a is equal to b. Now that I know what b is equal to, I can take the other function and plug in for b. So that's going to give me -2 equals 3a plus 2 plus a. And then I can just combine like terms, right? What's 3a plus a? Good. And then I would do what to solve? Subtract, which gives me negative equals 4a, which means a equals -1. Good. Sorry. Now how can I now find b, now that I know what a is? Plug it back into the first one. So that's going to give me 2 minus 1 equals b, which means b equals 1. So now I know what a and b are. So you can rewrite this as -1x plus 1, because a was -1 and b was +1. So now we know what function we can use that will make this continuous. So now we're going to go ahead and graph it. So on the yellow, this function exists where x is greater than 3. In the middle, in the orange, this one exists from -1 to 3. And then lastly, the pink is where we're less than -1. So we're here. So we're going to graph each of these pieces separately. The middle piece is linear, so I start at my intercept and I go down 1 over 1, down 1 over 1. I have open circles here and here. Now I'm going to graph the other pieces. So I have this piece here where it's at 2 anywhere that we're less than or equal to -1. So see how I filled the hole there? And then over here at -2, my function exists at -2 everywhere that we're greater than 3. So it looks something like this. And then you can connect this piece, of course. So have we now made the function continuous that we've adjusted? Yes.
So once you connect them, they become closed holes?
Yeah, good question. So it's not actually that they become closed holes. What's happening is, see how these two pieces are open? But see how this, when I go to graph this piece of the graph, it like fills that hole?
Yeah.
Yeah. So basically the other graph fills this hole that this one didn't fill. And then this one fills this hole that this graph didn't fill. So you're never going to have a situation where it's already closed and you're putting another closed one over it. Because that wouldn't be a function, because that wouldn't pass the vertical line test. So if it's going to be a function that's continuous, one side's going to have a hole, one's going to be filling that hole.
So can we just go ahead and fill it? So it's just easier on us?
Well, no, because you have to understand which one's filling the hole.
Well, yeah, well, obviously.
Yeah. See, I know you're not going to have different colored pens and markers and stuff on tests. So I'm not going to be looking at that. You just have to have a conceptual understanding of which of these two are filling the hole.
So like on the test, would you have to show that it's open with a hole in the middle or just
Mostly on the tests, you're going to be doing, it's mostly algebra based stuff. So mostly I'm going to ask you to find A and B. Okay. If I do ask you to do a graph, I'm more so going to be looking at the shape that looks like this than the holes. Alright, and the last one is just going to be like a refresher from something we've already learned where you're doing a graph sketch. Because I did notice on the test some of you guys forgot some of these rules. So basically on these two, when x approaches a finite value and goes to infinity, that means we have a what?
Asymptote.
Which type of asymptote?
Vertical.
Vertical. So we have a vertical asymptote at -2. And then we also know that when x approaches infinity and goes to a number, that we have a what?
Horizontal.
Horizontal. So right off the bat, I know we have these going on. I see here that this tells me that I have a point on my function at 2, 4. So I'm going to plot that. But this one tells me that as my limit approaches 2, it approaches 3. So right away that tells me discontinuity, right? My limit going to 2 doesn't match what the function is doing at 2. Do you guys see what I'm saying there? So that means I'm basically going to have an open circle at 3, because the limit is going to be approaching it from both sides but not actually touch the value up here. So over here, I can see that on the left of my vertical asymptote, we're approaching infinity, right? On the right, what are we approaching? Negative infinity. Now remember, we can cross horizontal asymptotes, so then my function's going to come up and go this way. Now why did my function go to the 3 instead of the 4? 3 is where the limit is. So because my limit says go to 3, it has to approach 3 on both sides, even though the function is defined at 4. So this is a point of discontinuity. We have two different types of discontinuity. We have infinite and a whole discontinuity. And then, of course, I want to make sure that we're approaching 0 when we go to negative infinity, which we are. We actually made it approach 0 on both sides. All right, I'm going to hand out your homework. Yes, what's up?
For this side, why is it going to 0?
It doesn't have to. I just so happen to make it. But you have options on that side if you wanted to.